Thank you. We want to finish the last half of the presentation on mass spectrometry. And I think this is where we ended up. We should at least be close to that. Because I kind of gave you an example of going to a conference and finding that the person had used a computer search, and it really wasn't relevant at all. You missed an awful lot of things. The computer made judgments. Computers don't make judgments, good judgments all the time. And anytime you start substituting a machine instead of people, instead of some thinking, you put yourself in real trouble and cost you very dearly. So again, the computer will always put out some kind of a response, but don't assume it's correct. Make sure you check that always. So at this point, I want to get into how we connect mass spectrometry to other instruments. It's really helpful if we can put a pure compound into the mass spectrometer. If you put a mixture in, these mixture compounds all explode into pieces, and you think, okay, how do I sort that out? And oftentimes the sorts get to be really difficult. So ideally, we want to put a pure compound in. My business is flavor, and so I may extract the flavor, the aroma compounds out of the food. I may have 200, 300, 400 compounds in that. If I simply put that aroma into the mass spectrometer, it would probably blow a fuse someplace mentally or physically. And so I have to have some way of separating and then kind of looking at one compound after another. And so I work with gas chromatography, I work with aromas, I work with things you can smell. And so gas chromatography is my choice. However, HPLC also works, so I'm looking at liquid chromatography, looking at things that are not volatile or have low volatility. One of the biggest problems we run into in interfacing any instrument with a mass spectrometer is the mass spectrometer works under very high vacuum. And my gas chromatograph has gas flowing through it, and that gas is going to go into the mass spectrometer. If I want my compounds to run there, that gas has to go and carry it. If you're working with liquid chromatography, you have liquid as a mobile phase, now you're pumping liquid into this vacuum. And of course, it destroys the vacuum. So we have to have one way or another to try and get rid of either the gas or the liquid that comes out of a chromatograph. And so, we have different approaches. At one time, this interfacing with the GC, the gas chromatograph, was really a challenge. Because we had big columns. They were, I call it quarter-inch big. That's a big column. And you had a lot of gas flowing through it. It might be 20 mils per minute, 30 mils per minute. Today, we use these very tiny columns. So while we finished the gas chromatography, and then you saw how tiny those columns are. They're really small, a few millimeters. And so today, we use much smaller columns. That means there is much lower flow. And we can actually make a direct connection. I don't have to do anything fancy with that. So for GC, it works out really pretty well. And so basically, that's just a picture that shows, yeah, here's an item column, here's going into the mass spectrometer. Not too profound. We do, and I'll get to LC, or liquid chromatography, in a moment. But we do have to have good pumping systems. And so we actually will work with either turbomolecular or diffusion pumps. We want to keep that around 10 to the minus 5th torr. So we're talking about 10 to the minus 5th millimeters of mercury. So that's one heck of a good vacuum. And so we basically work with what's called a turbomolecular pump. Basically, that turbine inside here spins around 20,000 revolutions per minute. It's trucking. And it will tend to pull vapors down, spin, so it pulls vapors down and tosses them out. And like I say, these small gas chromatography columns are around 1 mil per minute. But 1 mil per minute of gas here at atmospheric equals 10 to the 6 mils when you put it under a vacuum. Obviously, you put air under a vacuum, it expands. And so even the idea of 1 mil per minute slow carrier gas, not feeding much gas in, it ends up being quite a big volume once you put it under a vacuum. So you really do have to have really good vacuum pumps. If you don't keep a vacuum there, you blow your molecule into bits inside the mass spectrometer, those bits collide with air, and they neutralize everything. Basically, you lose your sensitivity. You must have a good vacuum system. And so, basically, your system, your gas chromatographic column feeds directly into the ion source, goes through your separation into your detector, and gives you some kind of an output. This is one I think I showed you already, and it shows up here as well. I just want to make another point of that. If you could see this chromatogram here, there's tiny peaks, actually 3 tiny peaks of orange up here. Right here, this is the rest of my sample coming through. This is time, this is coming basically out of the gas chromatograph. And there's 3 tiny peaks. And you may be inclined to say, okay, there's 1, 2, 3 compounds. But in reality, when this work was done, this was real work. That wasn't 3 compounds. That was 1, 2, 3, 4, 5, 6, 7, 8 compounds. Each peak was kind of the sum of 2 other things rolling along, or 3 other things rolling along. And so having each of these mixture of different chemicals confounds or makes it really difficult to go ahead and get any useful spectrum. So what basically the scientists, the researchers have come up with, here's this one peak, so it's this peak right here. We've got to look at it. That orange is the total. These are the 2 components, 2 different compounds that make up that peak. And they're just slightly, a little bit off time. The peak here for the 37 up there is a little bit before the peak for the 38. And so the mass spectrometer can say, oh, I got one set of ions that's going like this. They're all coming together, moving at a certain rate. And then there's another set of ions that follows a different pattern. So it separates those 2 different moving patterns and can go ahead and quantify them and determine what they are. And so if you look over here, this is basically what the mass spectrometer would give you. It would give you, okay, these are the ions that were moving together in one set. This is the ions that were moving together in the other set. And so it will then match this moving set to the other moving set and come up with some identities. It's really a benefit. Because, at that point, you don't need to separate components perfectly. If you can separate them by milliseconds, the mass spectrometer will measure them and measure them independently. And so it even makes separation easier because I don't need perfect separation. I don't need to separate it, by that much. Here's a peak, here's a peak. Nah, they could be under one shell, but just have to move milliseconds apart. So it's a tremendously powerful technique in a sense. HPLC, that's currently, let's say, the most exciting, the most innovation happening. If Pam were here, I could ask her about that. That's because LC is so far behind GC. That got recorded. Well, maybe she won't listen to the recording. I do tease about that. She loves LC, I love GC, so I take cheap shots with it. But this is interesting. So, gas chromatography has reached theoretical limits. It will never improve any further in separation. Liquid chromatography hasn't gotten there yet. And that's why we're seeing it as being really an area of innovation. It's kind of a little bit behind. It can make all these improvements, innovations even in the future. It is a problem that carrier flows are 100 to 1,000 times flows of a capillary GC. So I'm running a lot more material into that MS. Yeah, remember gas chromatography in mil per minute, that's it. Well, of gas, here they're putting a mil per minute or more of a liquid in, which expands tremendously. And so there has to be some way that we can interface, some way we can get rid of that carrier gas, that carrier liquid, or the mobile phase. And so there are different techniques: atmospheric pressure chemical ionization, electrospray, thermal spray, particle beam interface. Get a lot of innovation. How do get these things into that instrument? How to get these compounds in and not the mobile phase? And so this is electrospray. It's a very, very common source. It's probably the most common source. And so here we've got our liquid chromatograph coming off here. We've got a milliliter per minute or so of solvent. It comes into this section that's under atmospheric pressure. The needle here with 4,000 volts of electricity, the current here, it basically puts a lot of electrons out there. We get these particles, spray droplets. We get them charged. The solid will tend to evaporate into gas. And the positive ions then that remain will be drugged into the mass spectrometer here. So it's an opportunity to evaporate the solvent as it's flying along and just drawing in your positively charged ions. APCI, so that's one technique. APCI is somewhat similar. And so you may be using a gas coming in here too. But you have actually about 5,000 volts. So you may have your LC, or you may simply be drawing room air in, passing that through here, passes it through 5,000 volt corona charge, and that can be then ionizing the materials in there. They get drawn into the mass spectrometer. This is one that's used fairly commonly for a gas analysis. You know, we'll see them on air balloons, hot air balloons going up into the stratosphere, following pollution in Los Angeles or wherever else, because it's really a nice system for that. You can simply draw air in and measure pollutants in the air. I'm going to show you what I use it for in a little bit. I use it a little differently. Mass spectrometry also has another advantages for us in that we get kind of a chromatogram and we get then individual mass spectra as we go along. And like I say, we can select things in each of these spectra to look for, to monitor. So we can keep on monitoring composition of every peak as we go along. These are some, we're coming to an example for applications in a little bit. But we think about how we can use mass spectrometry to measure quantity. I talked about identifying components. We use it to identify unknowns. We can also use it to measure the quantity of unknowns. And so one of the best ways to do this, certainly in my field too, if I want to know how much of some odorant is present in a sample, this is an expensive way to do it. It cost me about $10,000 for my sample, my reference, my control. So, okay, I pay my 10 grand. I got, a couple micrograms of material. Okay, I can spike my sample with this stable isotope. I'm interested in flavor. Cherry flavor is a nice example. Cherry flavor gets its flavor primarily from a chemical, benzaldehyde. I'm interested in how much benzaldehyde there is in the cherry flavor in the sample. So I can synthesize for $10,000 a benzaldehyde that has deuterium in it instead of hydrogen. Now it's 2 mass units bigger. Instead of having 106 mass, like benzaldehyde does, it's 108 mass. Now I can then have my mass spectrometer, so I can add a known amount of this stable isotope to my sample. I go ahead and do my separation throughout the whole run. But I'll have this mass spectrometer only look at mass 106, and plot 106, and then 108. So what I do is I get an analysis of the same compound, the stable isotope or not, and I can look at the size. If the 106 and 108 are the same size peaks, then there's as much benzaldehyde in my sample as the internal standard. So it's really a good way, an internal standard is really a good way to go ahead and look for quantitative data. I'd love it if it didn't cost me $10,000 per sample. If my flavor has, 10 components, that's $100,000. There's 100 components, it's costing me $1 million. Okay, I'm not going to use it too often. It has to be something that's done routinely, and it has to be worth it. So, beautiful method, but exceedingly expensive to use. And this is an example. I said benzaldehyde. This is a dimethyl, it's a dimethyl group applied for uracil. And in this case, they went ahead and looked at a sample, looked at the masses of the two samples. This is your standard, and that would be a mass of 160. So you have a mass spectrometer coming along minute after minute, looking for a gas chromatograph or LC. And only when something has a mass of 160 does it give me measurement. And so here's my sample, here's my spike material. This I'm monitoring 178. So this is measuring the 5-alpha uracil that's in your sample. It gives me peak that day. Here's my reference that I put in the same sample. So I guess your internal standard is the same as the compound you're measuring. That's this string. I hope that makes sense. If it doesn't, we could try again. How's that? So let me know. Purity of a gas chromatographic peak. That is always the question. Is there something that's simply one compound? Is it you got a peak? Is it a mixture of 2 compounds, 3 compounds? Who knows? You really don't know. Your machine draws the line, and it doesn't tell you what's that they're reading. So, doing mass spectrometry, monitoring, looking for a mixture of compounds, looking is the compound present that you think is present. That's exceedingly useful function of mass spectrometry. We can also do 2-dimensional mass spectrometry. So what we do is we take a mass spectrum of a compound, and that will have all kinds of fragments. But then you can select certain fragments and bust them into more fragments. So it's really neat, 2-dimensional. We do one mass spectrum, and then a second mass spectrum of each of the pieces. And what that reason for that is that when something blows into pieces, there may be several pieces that have similar molecular weights. Well, okay, if we got a bunch of pieces with the same molecular weight, how do I know what they are? What are those other compounds? What are those other pieces? And so by doing 2-dimensional mass spectrometry, you can do a really good job of ensuring what you have is what you think you have. And you can use it for quantitation. It's one of our most sensitive techniques for quantifying things. The quad mass spectrometry, triple quad, so there's actually 3 mass spectrometers put in a row. And so you do your first mass spectrum, then you select certain bits, fragments of the first one, you bombard it again, and do your second. So it's called the triple quad. But in fact, it does do what I'm saying. It takes a spectrum of each of your components in your spectrum. They are expensive. They're going to run you $250,000, maybe $500,000. It's a decent price. If you look at a normal mass spectrometer, a single mass spectrometer, they're probably running around 150. So we've added 100,000 to kind of get that second dimension. It's not bad. I'll show you some examples of this. And the first ones we're going to be showing tomorrow at the protein meeting. So it comes from Vidi. Any of you that know fellow in the research lab, Vidi Anandram Krishnan, I'll do it. Okay, he's a really good fellow. But this is his PhD research. And this is where I said I slipped something in on you. Well, okay, this is what I slipped in on you that I'll make sure everybody gets it. So it's basically this example. So we'll show an example here. We'll show an example of aroma released in your mouth when you eat. Look for identification of unknowns, a little bit of example there. Assurance of purity, adulteration as well. So we'll kind of give an example of each of these and how mass spectrometry is used in each of these applications. So, I don't know if you pay much attention. I hope you do when you eat. I hope every time you eat something, you pay attention to it and say, oh, that's good. No, that's not so good. You know, that tastes a little wrong. This is what I think is wrong. You know, how's that? Make analytical tasters out of you. Because in high protein foods, high protein bars, they can be really good. The day they're made, you pick them up at the manufacturer, they're absolutely wonderful. They have beautiful flavor, they put flavors in there to make them taste like cherry, cinnamon, lemon, you name it. But what happens about a week later, 2 weeks later, a month later, they start having an old protein taste. They don't taste as good anymore. And that lemon's kind of gone away. Where is it gone? It's really an interesting one to us. What happens when you try to flavor high protein foods? It's a problem to flavor them. And we've never had a tool to measure what happens to that flavor. We can see that I can analytically see that flavor going away. I can take that bar, I can take high protein food, I can extract the flavor, and it's gone. I can't recover it, but I don't know what happened to it. Historically, I've never known what happened to it. If you don't know what happened to it, you can't fix it. That's basically the point. And so we need some way to understand where that flavor went so we can try to stop that process. And so what Bidey did is, I had fun with that. He's a chem engineer from India doing his PhD. One of his first tasks was to go milk a cow. Huh? Okay, yeah, you gotta go to the barn and find a cow, just one cow, and you gotta do the milk. Oh, okay. What we want a model protein, something that we can have control, a single pure protein. And he had to get cow milk from a single cow because there's a lot of genetic variation in cows, and milk protein isn't the same for every cow. We mix it together. It's really a mixture. Same proteins, it's casein, it's beta-lactam, but they're slightly different compositions. So he had to get milk from a cow. Then he had to go ahead and purify it, which was interesting for him too, and ultimately ended up with pure beta-lactoglobulin. So that's the model, that's what he studies. And if you put beta-lactoglobulin into a mass spectrometer, electrospray ionization mass spectrometer, this is what you get. Beta-lactoglobulin is a mass of 18,276. And so here's your peak. There's your mass, 18,276. There's some other oxidation that's happened in the protein. For some strange reason, the cow puts a sugar that puts lactose in two places on that protein. So here's my pure protein. For some reason, okay, nature's put more lactose onto that protein, so it's higher mass. It's the molecular weight of lactose, bigger. So my protein is bigger. The cow puts two lactoses on. So that's basically Bidey's control, his starting material. Then what he did is he put that in the presence of flavor, a benzaldehyde, cherry flavor, or almond flavor, depends on how you look at it. So here's what we just saw. Here's the pure protein, no reaction. Here's the protein after we put a little bit of benzaldehyde in it. All of a sudden, a new peak shows up here. New peak shows up here. That should down here as well. A new mass. That mass is exactly the mass of benzaldehyde. Benzaldehyde is added onto that protein. It's called covalent bonds. That's in 10 minutes. 10 minutes of reaction. And we're starting to see benzaldehyde disappear, be covalently bonded to the protein. Here's the benzaldehyde after 6 hours. Our initial non-reactive protein is getting small, and the peaks where we have benzaldehyde are predominating. So we're basically showing that we can add benzaldehyde. We're showing that, in fact, benzaldehyde adds to protein. So where does it go? It's forming covalent bonds. If you happen to like something like mustard or horseradish, what happens, so Bidey in this case added allyl isothiocyanate. That is the character impact compound of horseradish mustard. And so here's our protein again. Okay, nice. And not overly clean. There's some things reacting. But which one happens? And that was only 10 minutes. Our protein, unreacted protein, has virtually disappeared. And this is an allyl isothiocyanate. 1, 2, 3, 4, 5, 8 or 9 of my protein spots and now didn't chemically react with only less of thiocyanate. The fun part is that now we're starting to understand, there is covalent bonding. Nobody knew there was. Nobody ever knew there was covalent bonding. They basically said, gee, the flavor goes away. Maybe it kind of loosely interacts. There's some hydrophobic pockets. There's some polar groups over there. And so they basically haven't understood. If we can understand, we can perhaps study it, and maybe we can do something about it. We can try to either block those sites or figure out how to keep those sites from being reactive. So it's really a fascinating tool, and we would never have had this knowledge if we didn't have the mass spectrometry that could manage large molecules. So again, only way we found this is having mass spectrometry. This is another one. This is, I like diet colas. Coca-Cola, actually. Okay, I like diet Coca-Cola. When you give me something that's sugar sweetened, it's it doesn't taste right. It doesn't taste the same. And probably half of you is exactly the opposite. Yeah. Okay. But we all have our preferences. You know, the neat thing is we're all right. You know? I don't mean we're all right. We're all correct. In the sense that if you like it, it's best. There aren't many fields where you get that choice, where you're always right. If you like it, you're correct. It's good. So anyway, we were interested in trying to understand better what happens when you put something like aspartame, this high potency sweetener, to the aroma. Because it is the aroma that really dictates a lot of what you see and smell when you're doing this tasting and drinking of beverage. So is there a difference in the aroma if there's no sweetener, if there's aspartame or sucrose? So is there truly a difference? There must be, because we're seeing a difference. And so what we did in this case is, here's our subject. He's sipping an orange juice in this case. Of course, it could be a diet cola. And here's our mass spectrometer. I usually say we stick a small mass spectrometer up his nose. Well, we don't really stick the mass spectrometer. His nose is kind of difficult. But this is a pipe that's sampling his breath. Every time he takes a sip, check it out. You swallow, you exhale. So what you exhale is what just went down here and comes back out. So what you sense is coming out your nose. And so this is measuring what comes out his nose when he takes a sip. Then you can start saying, what was he given up here? Here's olfactory region. What was he given as stimulants? So we can actually measure the stimulants, the aroma compounds, that come from either a sugar sweetened, a no sweetened, or an aspartame sweetened product. Then you can start saying, is there a difference? You perceive them as different. Is that you who just sense things differently? Or is there some physical effect of having sugar present or other sweeteners? We can start to understand things like that. Where is the perception? So we can actually look. And this is now a real example. So this is the mass spectrometer. It's monitoring breath. He is breathing. That's a good sign. This is his exhale breath. If he's inhaling, well, you don't get anything in the mass spectrometer. Exhale, inhale, exhale, inhale, and so on. And that's acetone. We all exhale acetone. It's part of our metabolism. So the machine is measuring acetone in our breath. Here's where he took his sip. And this is his first breath after he takes a sip. All of a sudden, the flavor compounds, the aroma compounds that were in that juice or in that sample, now are coming out of his breath. That's what your nose was doing. That's what the olfactory region was doing. And it's kind of fun to watch. Some of these things, aroma compounds, they're there very quickly and they're gone. Some other ones start more gradually and go as such. It's really a neat idea. You start understanding why people perceive things differently, because you can measure the stimulus that they were given. Purity, again, I kind of beat you over the head with that one. A peak, a nice peak, a beautiful peak, doesn't mean it's a single compound. I don't care how nice it looks. You really have to be certain, and you do that by taking a mass spectrum of that peak. Adulteration, certainly is this one place we look at a great deal. Is there something there that shouldn't be there? Is it an artificial component like it should be there in the real product? Is there pesticides present, contaminants? So again, when we start looking around, there's just a lot that can be done with the mass spectrometry. And I went ahead and cut out a few slides because I thought I would make up the time there, and I didn't. So much for that one. You've got some more slides there, and I don't, because I got rid of them. Okay, so much for that one. You just got cheated out of about 5 slides or something. But there's just simple other examples. I showed this tomato leaf put in front of the mass spectrometer, where it bounces off and measures what's on the surface. So that we look for pesticides, look for herbicides. We can look for any kind of residue on that fruit or on that apple. This is an interesting one to me. The idea that you can use mass spectrometry to draw images or create images. And this is an example of a cross-section of the brain and looking at how the brain or the composition of the brain across it. I'm not quite sure what we'd use that for, but anyway, you can actually get a chemical image, a chemical picture of how something varies, because you can start beginning and kind of take a scan and look at different spectra, different compounds. What's the distribution of compounds across some phase? This is one that's actually an encapsulated material. This is where orange oil used to be. And so it's a powder particle. Powder particles drop 30 microns, in case you won't see that. So it's a small particle. And we start scanning with a mass spectrometer. We see, okay, here's kind of what this oil is encapsulated in. It's a starch, it's a protein. And then this is where the orange oil is. And we can get a composition of orange oil. So you can take an image of a particle as small as 30 microns and look how that particle changes different structures of that particle. It's really a fascinating technique, like I say, to be using it to take images, kind of chemical images. And certainly, mass spectrometry is a growing tool in the industry and academic life as well. At one time, we used to pay an arm and a leg for a mass spectrometer. It was a good deal of money. Today, they're low enough in cost that people can afford it. And so the idea of $150,000, that's not unreasonable for what you gain from using a mass spectrometer. So one time, mass spectrometry was only in elite laboratories. Now it's come down to the point where they're available for many companies. They are easy to operate. They are computerized databases, so it doesn't take a high level of expertise. It does take a cautious mind, but you can still get a lot of data. You can operate these as almost turnkey systems. And so we keep on finding advances in instrumentation, ease of operation, specificity. There continues to be advances in the field. It's really an impressive area. It continuously changing. If you ever have any burning desire to learn more about mass spectrometry, I'm in 147 Food Science and Nutrition. Love to give you a tour, show you different mass spectrometers. I know you will all be there. I'm teasing a little bit. But it is really a useful technique and very powerful. And like I say, now I went ahead and cut out some. Maybe get a question or two. Yeah.
We have a question from Rob for the LCMS. So with the time of flight measurement, to improve resolution, you can extend the length of your chamber. Would you also be able to lower the voltage that you're creating your ions so that they have lower kinetic energy and lower speed?
Okay, you want better resolution of your mass spectrum. You know what you normally do, and there may be a tube like this. Well, you make a tube like that, then you put a mirror at the top, and it reverses it so it goes up and down. Okay. So now the pathway's gotten much bigger. If the distance is increased, it's easier to measure time difference. The idea, if you change the voltage, well, those are still going to move about the same speed, and they won't be resolved. Maybe they move a little slower, but they're still not separated because there's so little difference. So, no, it wouldn't help you to use the lower voltage. No. Okay. Anything else?
I have a question. So you had that slide that showed gas flowing through a column as it goes on.
Yeah.
And then it hits the vacuum and it increases to 10 to 10.
It's 1 million times greater
And
volume.
it is 6 mils per minute.
Yeah.
So is that how you can separate is by increasing, going from one rate to a second rate a whole lot faster? How do you get that? You showed that peak that was really more than a peak, and then they separated it by mass because there was a slight shift in.
Yeah, they don't separate the mass. They don't. Well, it doesn't improve resolution or whatever, but you just get to see fragments that are unique to one compound. They're all coming out at the same time, but you're simply getting to tabulate them and look at movement of it. So the answer is no, but you might want a greater discussion of it. Okay. So it makes more sense. Okay. Well, anyway, don't tell them I gave you time off. Okay. Have a good day.
So you know we did everything right, and there was like photo ops.
Protein, all the side chains,
Do you have any published? We're thinking about like watching photo ops for different computers, so trying to figure
Counters public. If you want to look
I just wanted to make sure that, like, if she was
Yeah. We never just give one. Yeah.